Welcome to this lecture on filter design, microwave filter design by insertion loss method. Now, as I said that we can specify, there are some restrictions on specifying the insertion loss. Now, once that is done and we have chosen some way to represent that, then we need to know how to design and implement the filter. So, I am now giving you the whole process flow, that first from the filter specification you need to understand that what will be the PLR or insertion loss requirement, what type of filter I will do, etc., etc., that we have already seen. Once we have that, we do it. This is an important step. So, this we will understand that whatever may be the filter, filter may be band pass, filter may be high pass, filter may be band stop, filter may be low pass. We always first do a low pass prototype design. So, the first step is important one, low pass prototype. This is unlike the image parameter method. Here whatever may be the thing, we have decided about what will be the insertion loss, which with polynomial will do, that means what type of filter I will use. Yes, and the pass band, stop band, it is characterized many times, it is not low pass, but we always start with low pass prototype design, that is why we are calling it prototype. Once we have done that, then we will do some operations called scaling and conversion to make it to the specification that the specifier or user has given. So, this is another important step in this microwave filter design, and finally, we will see how to implement it, implementation of that. That means, on a actual microwave circuitry, how we implement that. So, a filter design by insertion loss method mainly have these four important blocks. In any design you have this, that from specification you start, you decide something, then here you do first a low pass prototype design, then you have some scaling and conversion operations, and then finally you think how to implement it. If required, we will see that for implementation we need to, some minimization is required about the length, etc., that we will see. So, this low pass prototype design, here in this part already we have decided about type of filter, that means whether it is Butterworth or Chebyshev or elliptic or the linear phase, that we have decided. So, we are going here. Now, first we start with Butterworth low pass prototype. Now, please see that here we have a source, then we have a source resistance that we assume to be always 1, and then we have an LC circuit, and then we terminate it with a resistance load. So, the source resistance is 1, this is 1 ohm. So, we can say that source, we have assumed in the prototype always source impedance is taken as 1. Later we will see that we can go to any actual source impedance, but in the prototype we have this. Then this is a L, this is a C. In the series arm we put L, in the shunt arm we put C, and this. Now, this is a single section. If required, you can have multiple sections, etc. So, source impedance is 1 ohm, and also in prototype design the cutoff frequency of the low pass is taken as 1 hertz. So, omega c is 1 hertz. So, our and you see we have to design L and C, so that we get a low pass circuit with this cutoff frequency. And you see the number of elements is called n is equal to 2. So, that will determine the PLR. What was the PLR expression for the maximally flat? You see, for maximally flat it was 1 plus k square omega by omega c to the power n to the power 2n. So, here this PLR will take as, since we are taking n is equal to 2 and omega is already 1. So, 1 plus omega to the power 4. So, PLR we have specified, and it is realizable because it is an even function of omega. As not only that, it is a function of omega square, which is also required, that even powers of omega. So, it is omega 4. So, it satisfies, it can be realized. Now, let us look at what is the input impedance I am looking from the source. So, I can write Z in will be j omega L, well, then a parallel combination of C and R. Once I have Z in, what is the characteristic impedance? Immediately what is the reflection coefficient? I can immediately write that reflection coefficient will be Z in minus 1 by Z in plus 1, and once I have this, I can find out PLR. It is 1 by 1 minus tau square, and that is 1 by 1 minus Z in minus 1 . If you simplify, you get Z in plus 1 whole square by 2 Z in plus Z in star. Now, any complex Z is a complex, Z in is a complex quantity, Z in plus Z in star will be twice real. So, we know that we already have the expression for Z in. So, if you put Z in plus Z in plus, you see only the real term is this one, because this is imaginary, this is also imaginary. So, we can immediately write this will be 2 r by 1 plus omega square r square c square, and another term is this Z in plus 1 magnitude square, that immediately we can write that so now once I have this PLR expression, I can immediately find out what is PLR. PLR turns out to be 1 plus omega square r square c square by 4 r by 1 plus omega square r square c square plus 1 whole square plus omega L minus omega c r square by 1 plus omega square r square c square whole square to the power 4. So, this is the PLR expression from the circuit, from my this circuit I have found the PLR. Now, this we can a little bit simplify and see that this I can write as, because ultimately my actual PLR, the Butterworth PLR, that is 1 plus omega 4th. So, let me write it in terms of omega square, omega 4th and omega independent terms, etc. So, if we do that, you will get like this. So, you compare this with our PLR, our specified PLR, which is 1 plus omega 4th. This is Butterworth, this is the thing I got. So, now by comparing I can say that what is immediately is observable is what is the value of r, because this is omega square, this is omega 4th. So, 1 is equal to this, that means this should be this term 1 by 4 r 1 minus r whole square, that should go to 0 if we compare these two. So, r becomes 1. Okay. Then if I compare omega square terms, I see that this also will go to 0, because in our Butterworth thing we do not have this omega square, here we have, that means this should go to 0. So, I should get r square c square plus L square minus 2 L c r square is equal to 0. And by comparing omega 4th, I can see that L square c square r square should be 1. So, these are the three equations. R or this is r is already solved. So, I can put these values. So, I have two equations, I need to solve L C, that I can do, and if you do that you get C is L is root 2. So, I have solved, because you see in my assumed circuit there were unknowns L, C and R. I have found that R is equal to now 1, C is equal to root 2 and L is equal to root 2. So, this way you can do. You can see that always this part is true, that I have taken this is n is equal to 2. Suppose I have n is equal to 4. If I specify that okay, order n is equal to 4. So, that time we will have like this. this is 1 ohm, then I have another LC, so n is equal to 4. Then this side again I will have this R. So, this is L, this is C, this is L, this is C. I will find out what is Z in. From Z in I will find out what is gamma in. From gamma in I will find out what is PLR. So, I will have PLR as a function of omega square here, and I know that if I have n is equal to 4, what will be the PLR specification from the Butterworth. So, that I know it will be 1 plus omega by omega c whole to the power or 2n. So, depending on n here, n is equal to 4 means it will be 1 plus omega c 8, omega c is 1. So, it is 1 plus omega 8. So, you will have these expressions here, you compare. So, you will see that the non omega term, the DC term, that should be 1, and omega square, omega 4, omega to the power 6 will be 0, and the components and the coefficient of omega 8 term, that should be 1. So, by that you can solve, but obviously you see this is becomes a bit cumbersome. The process is valid, but it becomes very cumbersome if I go for higher and higher order. So, for large n the method is not very practical, but what people have done, people have tabulated these values, that people have solved it because polynomial is known, that is known. So, for prototype you see that we know all the source impedance 1 ohm, omega c, 1 hertz. So, I can solve for this. So, the table, it is tabulated. Now, the tabulation needs a bit understanding, that is why let us see that people have tabulated it in microwave books. You will see that in Pojar's book it is given that for Butterworth filters I have and they have given the values. Suppose if I have only one element, if I have two element, like that tables are available. Now, you see that when I drew it was L, C, R, but here these are G 1, G 2, G 3 etcetera. So, how to interpret that? So, the concept is this, that this is called ladder prototype. So, you have seen in any synthesis problem you have this type of prototype, because this is your reference, with reference to this you design. So, we know first element is like this, then in the previous case how I design, take this. So, you see that what I designed, that is called ladder prototype. Now, there are two varieties. You see in the first one I can have a series inductance, or I can have a shunt capacitance. Now, if I have series inductance, this is called ladder prototype beginning with a series element. And in this case, you see the nomenclature is this. I know that this is actually the resistance, but they call it to have this table general. This is your first element G1. Sorry, this is not first element, because in prototype always this value is known, R naught is equal to G naught is equal to 1. So, this they call it G naught. Then this one they call it G2. So, basically I can say G2 will be your, if you call it that G naught. So, this is G1, this is L1. Then this one they should call G2, this is G3, this is G4, and the last one will be how much, because we are starting here, there are n capital N order. So, this is an extra one. So, G n plus 1. So, this is ladder prototype beginning with a series element. So, you see that this is your L1. Now, this will be what, this you can call as C2, this is your L3, this is your C4, like that. There can be another variety, that ladder prototype beginning with a shunt element. So, in that case the circuit will be like this. So, here we see that R naught is equal to G naught is equal to 1, then this will be your G1, this will be G2, this will be G3, this will be G4, this will be G5, and this will be Gn plus 1. So, we can now summarize that. So, in both these cases what we get is Gn or G naught first stands for what? It is the generator resistance for first type. So, let me call that this is, let us say, first type, and this one let us call, that means second type. So, please note that when we have series element first, we call it second type. When we have shunt element first, we call it first type. So, with reference to that, you can write that. So, in the first type, when I have shunt here, what is this circuit? This so I need to change this circuit, because here generally they, in the second time, they do like this, that instead of a voltage source they represent a current source here. So, that means here we will have G naught is equal to G naught is equal to 1. So, in the second type, this is a conductance. So, we say that generator conductance in the second type. Then what is G n plus 1? This is in the first type, it is load resistance if Gn is a shunt capacitance and here load conductance if Gn is a series capacitance. Please understand that here it is ladder network. So, this Gn plus 1 what it is, it depends on depending on the number. If I have finished with the previous one Gn, if it was a shunt capacitance, then this will become a load resistance. If it is a series capacitance, shunt capacitance and series, this is not capacitance, series inductance. If this is a series inductance last one, then this will be a conductance. Okay. And in general, so these are the two n values. What is in between? Let us call that Gk, where k is varying from 1 to n. So, this is inductance for series inductors and capacitance for shunt capacitors. So, the moment that has been done, you see this generalization now looks meaning. They have specified various values as we will take. Now, it is up to us which design we are following. Accordingly, we will choose whether it is an inductance. If it is inductance, this is capacitance. If it is capacitance, this is inductance, this is capacitance, like that. It is alternate. So, we will see, suppose you can have a design that a maximally flat low pass filter is to be designed with a cutoff frequency of 8 gigahertz and a minimum attenuation of 20 dB at 11 gigahertz. You know, that means he is specifying that what is your pass band, how much you are, and in stop band how much is the thing, how many elements are required. So, you can go on do that. We will have a tutorial there, we will see this problem. Similarly, you can have Chebyshev filter design, prototype filter. So, let me just briefly say this, that Chebyshev low pass prototype. So, again omega c is 1, only thing is the PLR is now 1 plus k square T n square omega. Now, T n, this Chebyshev polynomials, they have a property that T n 0 is equal to 0 if n odd and plus minus 1 if n even. So, accordingly, your PLR will be 1 at omega is equal to 0 for n odd, you see n odd, because if n odd T n is 0. So, PLR becomes 1 and this will be for n even, it will be 1 plus k square at omega is equal to 0 for n even. So, it is up to you to choose that, if you choose the n value, because n values will come from all those specifications that in stop band I want at least this much attenuation, in pass band I want this. So, from that n will come. The moment n comes, you can choose what is the PLR value from there. So, for the n is equal to 2 prototype, you can now find out that, suppose if we choose n is equal to 2, let us say. So, for n is equal to 2, you can see that T 2 x, the Chebyshev polynomial second order, that is 2 x square minus 1. So, PLR will be immediately 1 plus, you see it is n is equal to 2. So, n even, so T n 0 is plus minus 1 and it is 1 plus k square. You see n even 1 plus k square 2 omega square minus 1 whole square. So, that is 1 plus k square 4 omega fourth minus 4 omega square plus 1. So, already we have seen that won't change, this our basic, this if we have assumed this design. Where is that? No, not this. Where is this one? This is the same design. So, from there we have chosen that Z in etcetera. So, that expression finally we have derived what is the PLR, this expression PLR. This is for that design. So, this is one side and then for Chebyshev we have this. So, you can equate, that means I am writing that 1 plus this one, this equal to, I can write that 1 plus, already that time we have derived this 1 minus r whole square plus r square c square plus l square minus 2 l c r square omega square plus l square c square r square omega 4. This already we have done. So, now you can compare and from that you can find out various values. So, at you know that at omega is equal to 0, k square is 1 minus r whole square by 4 r. So, from here you can solve for r as a function of k square or k. So, k is what? This is for n even. K is what? K is the ripple level. So, that will be specified that I want ripple not to cross this. Once I know that, I know k value. So, I can find out r. Similarly, can do. So, these things can be done at hand. So, maybe in exams etcetera will tell you to do for these small values, but if larger ones we do n is equal to 3, n is equal to 4, n is equal to a, we will give you the tabulated values, the relevant G1, G2, G3 values we will give. Okay. But you understand, so that you can find out from the table which G you want to apply, what is your ladder prototype etcetera. So, now you see that if you specify some k value here, then r is not 1, as was the case in the Butterworth. In the Chebyshev, the r is not 1. So, r has some value. That means, you see from the basic design there is a problem that where is that? Yes. So, I have taken this as 1 ohm, source impedance is 1 ohm, but your this r, that is not coming as 1 ohm, it has some value. So, there will be some reflections here. Also, depending on that r value, Z in may not be 1. So, there may be reflections here. So, filters generally are not matched. You have faced the music in image parameter based method. Here also there will be mismatch, but I again refer you to the 9th lecture of basic tools of microwave engineering, where we have learned how to tackle impedance matching problem. So, you can always design with this filter a quarter wave transformer, or you can also add an extra additional filter element. Suppose you are having n even, you see this problem comes in n even, but if n is odd, then this is not there, r is equal to 1, that we have already seen. So, you can also do that, because for odd n, r is always 1 for Chebyshev. So, you try to make n odd there. So, you can design for various ripple values these tabulations are available. You should know, you should not memorize or think this, but if you understand this simple concept by which you can design this. For other filter types also the tables are available, or you can make your own table once by programming etc. you can first make, and then you can go on designing whenever the need arises. So, this makes the whole thing straightforward, that whatever may be the filter you first design the prototype. Now, we have not covered that actual filters will not be like that, it will be either high pass, it will be or band pass or stop band. It also its cutoff frequency is not always 1 hertz, it will have some other values. So, source impedance also need not be 1 ohm as we have assumed in the prototype, it can be any 50 ohm, 100 ohm, those are typical values. So, now from this design, once we have got this prototype low pass filter, we will next learn in next lectures how to scale up that and how to get the actual filter things, that is called filter transformation, that we will take up in the next class.